Last time I have given you the idea of transformation, and I have also given you one example to complete. Now, during the entire lecturing that I have done so far, I told you right in the beginning that in practice we get three kinds of problems. Three: equilibrium problem, time independent problem, time dependent problem or propagation problem, and then eigenvalue problem. Eigenvalue problem or specialized problem, they are valid only for certain parameters, certain particular. So, they are now. So, we have given you, at least now you have got some idea about the first and the last, that is the equilibrium and the time dependent problem. Eigenvalue problem, we have not done anything in analytical form. So, I just thought that let me do a simple problem of eigenvalue type. So, that at least all the three types of problems will be covered, and then after doing this I intend, because so far I have dealt with problems that are second order, yes, that involves second derivative in space coordinate, second derivative, and therefore, the weak form was always first derivative, and therefore, continuity requirement was always only on on the basic variable, because first derivative means the basic variable. Continuity, the quantity must be, if d phi by dx is there in the weak form in the integral, then the requirement is that in order that integral exists, you must have phi continuous. Such formulations are called C0 formulations, C naught formulation, C0 because we require only the continuity of the basic variable. So, we have done, and large class of problems belong to this category. So, C0 type problem, but then I think the real problems in solid mechanics, especially not, I will not say solid mechanics, because solid mechanics means it is, when we say solid mechanics, we are dealing with solid, that means continuum problem, that means problems which wherein you are trying to find out the movement of a particle. That means, a point P is having a displacement u v w. So, you want to see how does this point move with after deformation or with respect to time. But then there are problems which are called structural mechanics. Solid mechanics is general elasticity problem, 3-dimensional problem, 2-dimensional problem, where then we have structural mechanics problem, wherein for a specialized form of structures, specialized form of members, we simplify the equations, of 3-dimensional elasticity. Like we have got theory of beams, theory of plates, theory of shells. So, these are all structural mechanics. Here we make certain assumptions. They are special solids, they are not general solid, but a beam is a special solid. It has got a one dimension which is very long compared to the other two dimensions, then the load is applied in a particular manner. Similarly, plate, shell, frame member, all these things that we, so they are structural mechanics. And unfortunately, the behavior or the equations that govern the deformation pattern of these elements, they are not governed by the second order equations. Like beam itself is 4th order differential equation, plate is again a 4th order differential equation, shell is a 8th order differential equation, shell, and so on. So, all these are having higher derivatives in space. So, there the continuity requirement will be higher, because if it is a 4th order, then weak form will be second order, and for second order the continuity requirement will be second order inside the integral means continuity requirement in order that you can evaluate that integral, that at least d phi by dx 1 less than second, that is the first derivative also must be continuous. So, such formulations are called C1 continuous, where continuity requirement is on first derivative also in addition to the basic variable. So, C1 continuous. So, there are many problems which fall under C1 continuous. Of course, C1 continuous formulations become little complicated. So, now of late there has been effort to see whether such problems can be solved using C0 elements, and it is possible, we have done it. So, that is there, but is still in the classical form we should see how to deal with such problems which are where the space derivatives are high. So, that one is still remaining, and then so I will take a simple vibrational problem, and for that I just was thinking what to take for a simple, then I hit upon a problem that is given in this Sheshu's book, P. Sheshu's book. So, it is a simple problem that he has solved. So, I thought let me discuss that. So, it is axial vibration of a rod. We have already done axial. The governing equation for axial vibration of a rod is this. This is for axial deformation of a rod. If this side is 0, right hand side I have just suppressed it. If it is 0 right hand side, then this governs the behavior of a rod and under action of loads. So, u is a displacement deformation, and then now right hand side is now it is also having derivative with second derivative with time. So, I think we had done this type of problem when I dealt with finite differences. Yes, finite differences, that is second order transient problem. It is second order transient problem because time derivative is second. So, it is a dynamic problem. So, if you assume a harmonic solution, if you assume a that means u x and e to the power of, that means this is something like separation of variables. So, this is we also call it separation, that means u is a function of x and t, space and time. So, we express this as a function of x and then and times, that means product of function of x and function of time. So, we also call it separation of variable. We solve some such problem by making use of separation of variables method. This is, and if you substitute this over here, what we will get is this, which is only a in x. So, this is a x part, the part that that is relevant for u x, we get this equation, and we see here that of course, this we have dealt with, this you knew earlier also. Now, we have got here an additional and times u, and right hand side is 0. So, this one is a homogeneous second order ordinary differential equation. This is second order, u is, there is no non homogeneous term, there is no load term. So, this is a homogeneous, the solution now homogeneous, and solution of this will be infinite. So, you have to find out what for what value of omega the solution exists. The solution will exist only for certain values of omega, not for all values of omega, because here you get infinite number of solution, because this is homogeneous. Just like you have homogeneous algebraic equation A x equal to 0, it has got x equal to x vector will be infinite, and you do not have unique solution. So, here again we will. So, now I think this part is known to you, I have already must have spoken to you earlier also on this. So, then if you write down the strong form of this, strong form is just multiply this equation by weight, integrate over the length L, entire length first. This is okay na? This is strong form and weak weighted residual statement will be something like this. Weak will be So, this is the weak form and we are dealing with weak form. Under the integral you have got only the first derivative. So, therefore, your continuity requirement on u will be only on u and that is called C 0. So, we are dealing with all C 0 continuity, C to the power continuity to the power 0. Basic variable must remain continuous, that you must see. C 0 continuous, it is called C 0, it is written C 0 to the power, some people also write subscript also C 0, anyone, superscript or subscript C 0 continuity. Okay, we know that this u, now if you, because this is only a, so if you take a simple two noded you know, if you discretize this entire domain into number of smaller two noded. So, then we can have this expansion of ux like this n 1 u and n 2 u 2 and then weight can be fixed at, because there are two nodes now. So, it will be n j, weight for node number 1, weight for node number 2. So, this is our standard practice, we are not doing anything new, we will just see what is the form of equation that we are getting, that is all. I am just trying to show you, many of you must have already got it. If you did, I have done it with reference to finite differences, but not with reference to finite elements. So, now, here of course, n 1 n 2 is this one, this is what I was writing it here after I came till you people arrived here, I was just writing. So, that I can save some time. So, this is n 1 and n 2 will be simple like this, and we can write the two weak equations corresponding to the two nodes of a discrete element like this. So, this is first equation corresponding to node number 1, B t at 0, B t at L, boundary term. By the way, this term B t, boundary term is A e du by, what is this A e? A e du by dx, yes, it is a force. So, it is a force term, because this is strain multiplied by stress multiply area of cross section, force, the force. So, this has a force. So, you can also interpret this B t 0 and B t L when the weight will become, because at both these places weight will be 1, then this is the nodal force at nodal forces, because this is will be nodal force at 0 and nodal force at L, force P. So, this is force. By the way, so okay, so now let us do it further. So, this is, so the first equation looks like, I think let us keep this over here. So, the first equation we can write, this is, so if you call this B t as, so P 0, minus, now keep inside as before, quantities which are independent of x in the outside the integral. So, u 1 and u 2 will be can be taken out, and what we will get is this. So, we can have integral it is better to do it 10 times, so that you ds dx times u 1, this times u 1, then another term is there dn 1 dx a dn 2 dx. So, this is, if you could take this as a row, then this multiplied by u 1 u 2. So, this is a 1 by 2 and this is 2 by 1. So, that the first row can be written like this. First row can be written like this here, plus we are left over here. Now, here it is, so whatever, so we have integral and u 1 u 2. So, n 1 this row a will be there. So, I will just take omega square outside n 1 integral rho a n 1 dx, rho a n 1 dx, and again next one again omega square outside n 1 rho a into. So, this is 1 by 2 multiplied by u 1 u 2. This is the second row. First term will be, but n 1 twice it is coming in square. I am just putting here, that is equal to 0. And similarly, in the same way the second one also will be, this one will be, because this is P L, let us call it, plus omega square n 2 rho a n 1 Yes. So, this can be, these are the two equations which have been written, weak form, weak equations. Now, they can be combined and written in a matrix notation now, a 2 by 2 system, because we have written it in a simple. So, it will be this term, this one we, if you define this n I n j, because this one is n I first row I, second row 2 j I equal to 2, and this is changing from j equal to 1 2. So, this can be n I n j and derivative of this. So, I will call it k. This one is k 1 1, k 1 2, k 2 1, k 2 2. So, if you write that as k 1 1, k 1 2, k 2 1, k 2 2 times u 1 u 2 plus this omega square is there, omega square is common here, and then this one is there. Now, this is n 1 n 1, n 1 n 2, n 2 n 1, sorry, n 2 n 1 and n 2. So, this is n I n j, and in between this row A is there, density into area of cross section, master. So, that is, so this is, so I can write it as plus omega square, we can call this as m 1 1, m 1 2, m 2 1, m 2 2 times u 1 u 2 times u 1 u 2 equal to 0. Of course, 0 is means 2, it has to be 2, 0, it is a 0 vector. So, all right. So, we have got this. So, discrete form is like this. Now, so each term we know, I think we can compute our k, compute our m, and then for the entire domain we can always do summation, whatever we have done for one element. So, summation will work because it is a weighted residual. So, like this, here if you do the k, for example, k, so k I j, and m I j is n I rho A n j dx. If you compute this, k will come out to be what? As before, these are the strain, this is B matrix, derivative of n is B matrix in our so this is k will come out to be, so it will be A by L each term can be evaluated, and this one m the 4 terms of M, that comes out to be A by L common here. To 1 rho A L omega is, yes, rho A L by 6, rho A L by 6. That has to be integrated twice to 1, 1, 2. This is your matrix. By the way, this matrix is that we have is called consistent mass matrix, consistent. Because we have derived this in a quite a logical manner by using weighted residual theorem. We have not done any approximation. So, this is consistent. Why it is called consistent? Because it is just a mass matrix. Why the word consistent? Why? Because when it is started, people were not deriving, they were directly putting the mass at the nodes. If element is there, just from physical considerations, half of the mass of the rod will be put at the 2 nodes. So, people were working even without this derivation, just by putting the mass, lumping the mass. That lumping was very prevalent even before the derivation came in practice, before derivation. So, people were used to that kind of mass matrix. So, when people knew this or became little more knowledgeable, and then they said it can be derived in a consistent manner or in a formal manner, then that mass. So, then they said okay, that mass is a lumped mass and this one let us give it consistent mass. So, that is how, otherwise this is simply a mass matrix. And from then people said okay, there are situations when you cannot or you should not, I mean it is much better to deal with lumped mass matrix than consistent mass, because we want the equation or the system to be decoupling. So, they wanted a diagonal matrix. So, I told you for example, row sum. So, if you want lumped here, lumped mass, so row sum will be three 0 0 3. Here both the degrees are of having the same dimension. So, there is no problem. It can be, and therefore, it will be rho A L. Now, here you can give a physical meaning, rho A L by 2 1 0 0 1. Now, you can see here what is rho A L by 2. Rho A L is the total mass density, area of cross section into length of the rod is the mass multiplied by mass density. So, total mass divided by 2. So, this mass was lumped and put over here. So, lumping, and this is rho A L by 2, rho A L by 2, and this was made 0. Diagonalization has to be done, because there are 2 ways of doing diagonalization, because now one is You can do diagonalization right in the beginning from physical consideration, directly lump the masses at the nodes, but then you are not deriving the basic equations. So, but if you are doing in a consistent manner, then you will get this matrix, then you are getting this matrix. Then how to, because but I want my matrix to be diagonal. No, equation, you see, it has been proved that diagonalization, in fact, you see, just like, because we are talking of second order, the differential equation. There is something called stability of the differential equation. Just like we have a stability, that means how stable will be the solution for that differential equation. So, it has been proved that diagonalization, in fact, improves the stability of the differential equation. The solution will be much more stable of the governing differential equation by this diagonalization. And certainly, it slightly changed, but it changes for better, diagonalization.
What about the equation?
What about the equation?
Accuracy, means consistent.
Accuracy. There are those people who have no practice, they will always say consistent mass matrix will give you good result, but it is just the reverse. Diagonal, this lumped mass matrix gives you good results.
And better stability also.
Lumping always improves the stability of the system, lumping. So, otherwise, so this is row sum method is a very simple method, but then there are later on it has been formalized, because when people saw that diagonalization helps, then they said, supposing there are degrees of freedom. Now, when we will go to beams, you will find that the nodal degree of freedom will be displacement as well as rotation. So, there will be one rotation, one displacement, one rotation, one displacement for two noded beam element. Now, it is a 4 by 4 matrix. Obviously, each term is having different dimension. Two terms are having, because so dimensionally it will not be correct too simply. So, blindly it cannot be done. So, we have to see that mass in the diagonalization process, you have to see that mass is always conserved. Mass of the element, for example, here we see that diagonalization is making, yes, m by 2, mass by 2 at the 2, mass must always be conserved of the element. Whatever you do, you should see that mass is conserved. Element mass is, total mass is somehow distributed among all the degrees of freedom which contribute to translation, one type. If it is moving in one direction, then all the degrees of freedom will contribute to that mass. If it is moving in this direction, then these degrees of freedom will contribute to this, but not the rotation. So, now it has been formalized, and a very simple paper was written by Hinton, Pica and others. Now, it has come in a book form, in this one, in Oden's book, sorry, not Plesha, not Oden. What is that book? Finite red color book? Cook, R.D. Cook's book. So, Cook describes the diagonalization for a general beam or plate. So, those of you who will be ever interested in this dynamic problem, please look up Cook. He makes use of the original that paper that has been written. Okay, so this is this is at the element level. We got this. We have got now that yes, we have got that k element times d element. Of course, I am just writing this d. dE means 2 degrees of freedom equal to, for the element Yes, this is okay. Yes, yes. Signs are okay.
Yes.
Signs is all right, because this one was negative. This is this was negative. So, I have just taken it on one side. Everything was 0. This plus this minus this was 0. So, I have just taken negative on one side. So, this is the for
Omega square will not?
omega square. Yes, certainly omega square. Yes, omega square. Omega square is there. Yes. So, this is now once you assemble, all number of elements which are joined together, and then such terms will come. I have always been telling you that yes, they will come, they will always nullify at any common node, plus minus this will be, and only at the end, yes, at the end of the, if this is the total assembly, everywhere else it will get nullified, but when it comes to the end, it will remain here. And so, here at 0, let us say call it as here P 1 and here P fine, P initial, let us say P initial and P final, this will be there. So, P, this will be plus and this will be minus, rest all will be zeros. But then when we are doing free vibration analysis, there are no external forces on the system. So, in free vibration analysis, there are no external forces. So, both P I and P f, and therefore, you are dealing with K E D K D equal to omega square m d, and this is an eigenvalue problem. This is a generalized eigenvalue problem, like A x equal to lambda b x. This is a algebraic eigenvalue problem. If you see any book on what is eigenvalue, so this is A x equal to b x lambda b x. So, this is a generalized eigenvalue, algebraic eigenvalue problem. And we will have to solve. We will have to solve for various omegas, and there are number of methods. I will suggest that I will cover some of these, but I think to be on you read from his book, because he has put them in brief. So, if you see here, there will be solution of eigen pairs, solution of eigenvalue problems. Solution of eigenvalue problem, that is, there are three, he writes that there are three ways to find out eigenvalue, that is, one is determinant based, obviously one is, we all know determinant must be 0. So, other one is transformation based, and the third one is vector iteration based. So, these are the three methods, and these are described here in brief. Of course, there are books only dealing with eigenvalues only, solution of eigenvalue. So, please go through this carefully, you can take Xerox and you read it. This is the book by P. Sesu, Please issue page number 257. Page 257, you can just see this method of eigenvalue solution. Okay. Now, this is important, just like solution of algebraic equation, method solution for eigenvalue problem, because ultimately we will have to solve this. So, you please read it. Now comes, as I told you, that we have this.
Previously, we have solved MD double dot plus KD equal to 0.
MD double dot plus KD equal to
0. That is the same problem.
Pre-vibration problem, second order.
Previous class we have solved the same.
Yes, but MD double dot DC, that is the dynamic problem, because D is still a function of time. Now, that can be made a function of only space by writing it d bar e to the power of I omega t. So, that x and time will get separated. So, ultimately it will be only a function of, because when you have to solve it, it has to be brought in algebraic form. Okay. But general, yes, any dynamic problem governing any, most general problem is, this is our, yes, KD. I mean, if you want to put also damping, then this is your, yes. But here all these are functions of time. Now, we are saying, yes, dt can be written as, because here it is a dt. So, dt can be written as d, which is, yes, times e to the power of I omega plus. Okay.
We can find out D in terms of x, and afterwards we can substitute.
Afterwards, you have to substitute here in order to get, yes, solution in time, because this will be multiplied. So, this is
Again, in this we will need the value of the omega.
omega only. So, when we solve,
Again, it's the eigenvalue.
so that what I am saying, omega. So, omega is these methods that I told you, these are meant only for solving omega. Omega and d also, corresponding to each omega, you will be finding out also d,
The eigenvector.
eigenvector. So, each pair, that is eigenvalue and d, we have to find out. So far we have taken that, yes, these loads are acting along the, but now here if this is you have a rod subjected to transverse load. So, it bends, not only there is axial deformation, but there is a bending, there is a rotation of the smaller element. And the governing equation for this is this, E I d fourth w dx fourth, if this is p x per unit length. Now, I think it is all right if I take p upwards positive. So, everything is okay, this sign is okay, p x. So, this is the fourth order. So, any displacement here, or if you want to study the vibration of a transverse vibration of a beam, that means like this, like this, like this. transverse vibrations, then it will be given by then what? Rho A, no, it is not rho A, because it will be curvatures. Moment of inertia comes, but anyway some mass parameter will come, and then it will be dt square. So, that will be the time dependent problem, and this will be the static. So, first we will study this, how to take care of this. Now, this is okay, this is fourth order. So, strong form weighted residual statement for this will be weight multiplied by weight E I d fourth W dx fourth minus weight P and integrate. No, I am talking of this. See, because you have to start with the statics, na.
So then how Px is going to depend upon m d2 omega by dt square?
I am not saying that. These are the two. I am talking. This governs the deformation of the beam, and this equation governs the vibration of the beam. These are the two. This is the vibration of the beam. This is the deformation of the beam. So, this is the strong. So, please do now you try to get the weak form of this statement. Strong is there in the given form. Now, in the given form, the requirement for this will be the third derivative of W must be continuous. Is it not? In order that you can evaluate this integral, see, it is a question of integral. How when can you integrate this integral? The third derivative, because if it is not continuous, then how will you integrate? Fourth derivative will become, let us say it is, so it becomes 0. So, it will be null and void. So, it will not be. So, this is where is the problem. So, always remember that whenever anything is in the derivative, highest derivative, one derivative less than that must be continuous, then only we can evaluate this integral. That is the requirement. This will be, yes, you are right, this is a C3 continuous, in the present form it is a C to the power 3 continuity requirement. So, this is a C3, C to the power 3, this one C cube continuous problem.
It does not give any physical meaning to that.
No, I mean given equation is, see, mathematically yes, it is only continuity based upon the continuity requirement. C0, C1, C2, C5 etc. is called based upon continuity requirement. So, this requires Q, I mean third derivative continuity.
What it requires, we don't, you can say, what it requires by C3 continuity.
What requires means, see, my function that I assume, function, let us say W, I cannot take A plus, now of course, A is constant. So, that will not, A plus Bx I cannot take, even if you take A plus Cx square, that also, even if you take dx cube, no, dx cube, because third derivative, first derivative, second derivative, then third derivative, not. So, you will have to take e to the power. So, minimum requirement is that we must take this. You must take a quartic polynomial in order to evaluate this integral. That is
This was strong.
strong. Yes, this is in the strong form. That is why, but then we try to reduce it. We
Weak form, then we can.
yes. I mean, we try to always say that how to reduce this requirement. This is very high requirement. So, we must reduce it. So, we find out the weak form. The weak form is, again you please take this and this as two functions, do it integral by parts, integrate it by parts. So, we will get first term, that means first term will give you W x E I d cube minus both becoming W. So, that let us write this letter capital big W and this is small w. Third, last term there is no problem. So, that is
possible if we further weaken itself?
no, I am just no, you see here further. So, this is after doing one integral, one integration by parts, we have got this. And now physically what does this mean? This one is this third derivative of W, shear force at 0 and L at the two ends, that is that gives you. And
Is it, we can say curvature continuity is required?
yes, to evaluate this second derivative.
Curvature continuity.
Second derivative must be continuous now. At least you have reduced the condition from the previous. So, from this one now this requires only this is C2 continuous, C2 from C3 it has become C2. But I think we can further reduce it. We can further reduce it, capital W. This is boundary term, this is there is no integral here. So, this will remain as it is. L now minus. Now, I take this and this, these are the two product of two functions, derivative. So, first function into integral of second derivative. So, I will get another boundary term. So, it will be dw by dx E I and d square w. Sorry, this is small, d square w by dx cube. First,
dx square.
This is x square, yes. Integral, this is integral, na? Achha, no, this is boundary term. Oh, yes, this is boundary. So, this is also boundary, and minus plus, second, it will become plus, na? Now, second, I mean one, because this into this is integral. So, first derivative of this, that is second derivative of capital W. So, it becomes this x square E I into integral of this, that is secant of small w by dx minus plus is okay minus w p dx. So, there are two boundary terms now. Now, there are two boundary terms, this is one and this is also has come. Of course, second derivative of E I times second derivative of w dx square is moment at any. So, this is the moment at 0 L, this is shear force at the two end, and you can see here, see the work, see this represents work, this is a basic principle. See this moment does work on what? On rotation. So, if this takes a it is derivative of some derivative of weight, the derivative, that means rotation times moment. Now, here is what? Shear force does work on what? Displacement, shear force and displacement. So, this is the two are consistent. So, either you prescribe this or this, any one. So, it is a okay. So, we have got after two integrations, we have got this is our weak form. Now, if you do further integration, then I will take this as this. So, integral, this will become third derivative and this will become first derivative. So, I will not get any advantage, because in that case I will have to take my weight third derivative. So, I am just changing my weight to C0 C2 continuous. Now, this is what? This is C1 continuous and this also is C1 continuous. So, C1 continuity on C1. Why C1? First derivative. Continuous, second derivative inside the integral means first derivative must be continuous. C1 continuity. I hope you are understanding this. So, we stop here, we do not go further. So, this is our weak form for the beam problem. The weak form is this weak statement of the.
We should continue up to the stage where
both become equal. Both derivative of weight and derivative of your displacement become equal. That is the rule. Because beyond that there won't be any advantage. So, any problem you take, this is the rule, otherwise there is no advantage. So, we stop there, and then but then still we are dealing with C1 continuity. We cannot avoid C1 continuity. So, it is not a C0 problem, but it is a C1 continuous problem. Now, C1 continuous problem has its own what should I say, challenges, because it is the formulation is not as simple as that we did it for C0. Okay. So, we will now see how to discretize this kind of C1 continuous problem. Is it okay? At least statement or what is the purpose of doing this, is it clear? Because rest you can read, but then the basic idea you must understand. So, we stop here. So, this is my integral is this, load integral there is no problem, but this is the basic integral. So, actually this one will give you your K stiffness property, this one will give you, this will give you load term, and of course, these are the boundary term. And so, we will see how to deal with this C1 continuous. So, all the problems of beam, plates and shells are C1 continuous. These are called, that is why we call, we distinguish between solid mechanics and structural mechanics. Solid mechanics is C0 everything, because you are dealing with displacement, there we consider entire continuum. Solid, we consider a point, movement of a point. Point P has got a displacement u, point P has got a displacement u v w. Okay. So, there all the quantities are only you need only first derivative, but the moment we say no, one dimension reduces. So, I bring in the concept of rotation. I will be, because when we derive beam means you have to define what is rotation, and the moment you bring in rotation, this problem comes, and same thing happens in plates and shells. So, structural mechanics problems do pose this challenge of higher continuity requirement, and this has been the cause for development of so many elements. If you see the literature, you will find hundreds of elements for beams, plates and shells, because it is not, there is no uniqueness. Somebody will derive something, because that will not exactly satisfy this. You cannot, it will be only an approximation, and so there will be, we call it elements which do not conform, which are not conforming. So, we have got something like non-conforming elements. It is very difficult to derive conforming elements in 2 and 3 dimension. Conforming means which should satisfy all the requirement of continuity, all the requirement of continuity. In 1 dimension in beam I can do it, but the moment I go to 2 dimension it becomes difficult. So, then we have got something we will have to overlook, some continuity requirement. That means, my element is does not satisfy complete requirement of continuity. So, it will be a non-conforming element. So, if you read something, this word will come, non-conforming. So, the purpose of this course also is, that is, when you read, because you should go to now library, journals, browse through the papers, see. So, these words will come, non-conforming element, element which are non-conforming. So, in 2 and 3 dimension you will get non-conforming, because we will not be able to satisfy this C1 continuity requirement. But anyway, we will start with beam. Beam you can derive a conforming element, there is no problem, because it is 1 dimension, and then we will go to 2D and see what can be done.